Today is our great honor to invite Professor Yu to give us a lecture at our department seminar. At first, let me briefly introduce Professor Yu. Professor Yu is currently a professor and the holder of the G. Paul paper 54 professorship. He received his PhD from the University of Texas at Austin and worked as a postdoc in the Materials Science Division at the Lawrence Berkeley National Laboratory prior to joining the Texas A&M University. His research is closely related to energy conversion and energy storage and electrochemical systems. The specific research topics include lithium-sulfur, lithium-ion, and low-cost metal batteries, thermally chargeable supercapacitors, thermal energy storage with phase-changing materials, thermoelectric materials, and thermal transport in nanostructured materials. Let's welcome Professor Yu. So, Professor Yu, please.
Thank you, thank you, Professor Ouyang, and it's very pleased to have opportunity to give a talk and about energy storage and conversion. And so, yeah, Professor Ouyang is also, renowned professor in that field. So, I read some papers as well, and so I'm very glad that I have that opportunity. So I heard that this is a graduate student seminar. Is that right?
Yes.
Yeah. Hope that I'm not going too fast. Okay, I probably in the Singapore and the English is common language. So I hope that there's no problem, right? In general, right?
Yes.
Yeah. Okay. So I have about 1 hour, right? 50 minutes maybe.
Yes.
About 50 minutes. Okay.
Yeah.
So I will just briefly introduce what I'm doing and in my group. So today, what I'm going to talk about here is a thermally chargeable supercapacitor, as you can see here. And then I'm going to introduce lithium-sulfur batteries. So basically, a lot of topics in my group involves carbon nanotubes and also some graphitic carbon in other forms as well, and mainly for energy storage and energy conversion. And I have other topics like thermal energy storage as well. But I'm going to talk about these two topics. Probably time is kind of short. So first topic is for energy conversion and sort of storage together. And this is wearable electronics. Basically, whenever you wear electronics, you have to charge your cell phone and your Fitbit, smart watch and things like that. So this frequently requires charging, right? So it is a kind of cumbersome. So if you look at your body, and this is a thermal camera image, and so we have actually quite a bit of energy dissipated from our body. So in case that we can somehow utilize these dissipated heat and to charge some of these devices, and that would be fantastic. So that's basically the motivation. And so we are working on it. And I know that Professor Ouyang is also working on this kind of technology as well. And so I hope that at some point of time and somebody can develop this fantastic device. So one of the technology that we can work with is thermoelectric energy conversion. So essentially what that means here is if you have a conductor, electron conductor here, and once you have a temperature difference like this, you have a hot place and the cold place, for example, like that, and you always develop voltage because this is a electron conductor. So in this case, you do have a thermoelectric voltage developed, and out of that, and then you do have a temperature difference, delta T, and then it is proportional to, voltage is proportional to what we call thermal power or Seebeck coefficient. So for example, if you, make a sort of a thermoelectric engine like this, you always develop voltage, and if you connect the circuit like that, and then because of potential difference, you can draw a voltage current like this, and then you can put your whatever the charging device here, and then you can charge your, say, electronics. So there's actually one problem, and since voltage is proportional to this S factor, which is called the Seebeck coefficient or thermal power, and typically, this value is actually quite low, and this is the organic material is a 0.01 millivolt per Kelvin, or inorganic material is about 0.1 millivolt per Kelvin. So unless you have really high temperature difference, and voltage that you can get is tiny. So typical device requires about 1 to 3 volt, right? If you think of the dry cell, it's about 1.5 volt, right? Then under, say, 20 Kelvin difference, you need a huge number of these material and connected in series, so that you can boost up the voltage. But this is kind of impractical. It's too many, right? So still you can do it, but it's not that convenient. So our motivation, at that time was, then how come we overcome this? And the one remedy here is to have a large Seebeck coefficient. So we focused on that value, and we actually tried to search many different materials. For example, Nafion is a polymeric material that we used before, and so we actually measured, and it happened to be actually pretty large here, right? So this thermal power is about 4-5 millivolt per Kelvin, as opposed to conventional one is about 0.1. So you have quite large thermal power. So there is actually quite a promising characteristic here. But on the other hand, electrical conductivity is not that large. And this is a 2 Siemens per meter, which is many orders of magnitude lower than the typical thermoelectric material. So there's no, the material that have always a better property, right? So you have to pay the price, right? It's like our life, and if you have something good, and you have to give up something. So that's the problem. And then how do we utilize this and overcome this drawback? So what we have done here is typically conventional thermoelectric device. You do have an electron transport because it's hot, so they want to move away from hot zone. And same thing for ion, and ion is actually moving that way as well. The major difference here is that when you connect this circuit, then electron can get out of this material, and kind of making a loop in like this way and continuously. However, ion cannot get out. So in this case, what we are using here, and here we basically the ion. So previously, as you saw, and this material here basically use ion here. Okay, here's a proton instead of using electron in conventional thermoelectric. So in this case, we basically accumulate the ion in cold site, and since the ions cannot get out, and we basically use this as a capacitor. And so that's what we did. And in this case, we just want to make a kind of a attractive title. So we call this thermally chargeable capacitor or supercapacitor. That's what we actually named it. And so this is basically the motivation. And So if you look at the governing equation for that is basically ion transport whenever you have temperature difference. So this is basically the current associated with ion. And what was interesting here is actually this, kind of a complex, equation. But at the end of the day, what we need to do here is we are interested in the steady state operation, which makes this current zero. And then whenever we, say zero net charge condition, which is oftentimes the case, and then you end up with this. Okay, this S is what you have seen before, which is a thermal power. That is proportional to this alpha factor, which is called Soret coefficient. For positive ion, this is a negative ion. And so negative ion doesn't mean that it's a negative value. And positive, here is Soret coefficient for positive ion doesn't mean that it's always a positive number. So whatever those numbers are, and this value supposed to be greater to get this large S value. So that was our motivation. So to make those two far apart, and that's typically those alpha values a positive number. So we try to make one parameter as small as possible. That was our approach. So we actually tried many different materials at that time. And when we use a liquid phase ionic conductor, then your ions here actually move together. Positive and negative ions move together. So basically, the number of positive and negative ions about the same. So the voltage is actually proportional to the difference. But this is not that large compared to that. And if we have a polymer-based ion conductor, then negative ions actually tethered here, attached to the backbone. They are heavy, so they are not moving well. So only the mobile positive ion is moving well. So you do have a large difference in terms of number of positive ion. So in that case, we can develop much larger voltage for polymer-based ion conductor. And therefore, we focused on polymer-based ion conductor and for thermoelectric application, which is what we call polyelectrolyte. So these are all solid state. And so we tested many different ones, such as sulfonated peak. And we do have here is a positive ion here, proton. And it's about 3 to 4, something like that. So millivolt per Kelvin, which is good as well. So, since it has a pretty large backbone and the backbone doesn't move, but the mobile proton is moving, which is good. And so we developed the two different type of this capacitor. One is a planar type, and so that we can have a thin film, and we create the temperature difference along this thin film direction, in plane direction. So, the benefit here is that we can make a large temperature difference. But since it's very thin, and what we can get in terms of current is pretty small, and that's the drawback. And same thing here, and cross plane or outer plane. And so we can actually have device in this configuration, but we can have a larger current, but temperature difference is not that large. So as you can see here, because it's thin, so the voltage that we can develop is small. So always you have to pay the price, and always pros and cons. There is a trade-off, and so we developed two different devices. So the first one is a patch type and cross plane. So we made this device using carbon nanotube and graphene flower with the polyaniline polymer, which is called the redox polymer, and together with polyelectrolyte inside. And it's a capacitor like this. And you do have the hot side electrode and cold side electrode. And then this one contains a proton. And when top side becomes hot, then the positive ion is moving. And then we do have ion accumulation, so we can store the energy. Okay, so when we develop this and we try to understand the physics behind that, and so we propose working mechanism, and as I will show in the next slide. So basically, the material that we're using here is what we call polystyrene sulfonic acid. So we do have this mobile proton that is moving and across this temperature gradient. So thermal power is about the same, 6, 5, and up to 8, something like that. And then we develop this device here. So here's a working principle. And when we have a positive, here's a hot side here on top, and then this mobile proton, this negative one is a backbone, so it doesn't move. But this positive ion is moving because it's hotter, and so you have a higher entropy. They try to escape, right, and more energetic, and then this positive ions accumulated, and then when we connect the circuit, since here's a positive and electron is withdrawn from top electrode, that is because of this. We actually had this polyaniline polymer, which can donate electron or receive electron. So it donates electron, and then this electrode receive electron. So, and then this electron will be accumulated on the bottom electrode. And when we turn off this temperature gradient, and then they actually return like this and disconnect the circuit. And then this electron is accumulated in one electrode. This is basically the energy storage. So this is basically the working mechanism. Okay. So I hope that this is a kind of straightforward. I hope. So this is actually quite simple, device. As you can see, this is the electrode, a carbon nanotube electrode. We have a polystyrene sulfonic acid, and we actually stack them together like this. And this is a basic device. It's very simple, and simple is better. And because these devices should be very low cost, and we can actually make multiple and connect in series and parallel, and we can actually do many different things. So this is a carbon nanotube only, and electrode, and this is when we actually mix with the graphene flour like a graphene, becomes very porous. Since it's a capacitor, we need to make an electrode porous so that we can have a large surface area, and then we can incorporate this polyaniline, and we actually use electrode deposition and to make a very thin film of a polyaniline on top of that. So that's basically what we have in terms of electrode and in terms of device. So this is a capacitance, and because it's a capacitor, so when we have only carbon nanotube, it's not porous, so capacitance is not that high. But when we have graphene, and then becomes a little bit higher, when we have polyaniline, which is a redox polymer together, and this becomes a pseudo capacitor, and then the capacitance becomes really high. So that's what we have developed. So this is a thermal charging and discharging behavior. So when we have a temperature difference of 5 Kelvin, there's a potential here. And when we have, one side is hot, and what happens here is the proton is moving, and then the voltage is actually going up like this. And then when we discharge, okay, we connect the load resistance, connect it, and then the electron is withdrawn because of this positive ion here, and then the voltage drops, okay, like this. And then when we disconnect this thermal gradient, and then it actually goes back, the positive ion goes back, and you have electron on the bottom electrode, so voltage becomes negative. Actually, it's the same as this, exactly opposite here. like this. So this voltage here can be stored for long period of time. And 24 hours, one day, without too much trouble, this is just a store. So what that means here is that we can use this when we need it. So basically, this is how we actually charge those capacitors using thermal energy rather than electrical input. Okay, that's what we have done. So, but still, the voltage here that we can have with a single device is only 40 millivolt, which is not good enough. And this is 5 Kelvin, which is good for body temperature, but it's only 40 millivolt. It's not that great. So I need a 2 volt so that I can operate device. So that's why we developed the planar type thermally chargeable supercapacitor, because we can actually make a larger temperature difference. So in this case, what we use here is graphene oxide. And graphene oxide has a proton, okay, because of this hydroxyl group and carboxyl group, okay, hydroxyl group, carboxyl group. We have a proton that is migrating and between the layer of graphene oxide. But this number of proton is not good enough. So we added more by putting sulfuric acid in between, and then we can raise the concentration of this proton here. So we have pretty large number of proton here, and we actually measured it, and here. So we actually increased the proton, and then we tested it here as well, and using our experimental apparatus, and the thermal power becomes about the same, and as well. But in this case, so we can create a large temperature difference here, so that we can raise the voltage. That's what we are doing, and at that time. So in this case, what we use to make that is, here's a graphene oxide, and we actually have a sort of a drop casting of this solution, because the graphene oxide is soluble and dispersible in water pretty easily. And then we actually drop cast, we dry it, and if we use a laser and scribe it, and here becomes reduced, and then this becomes electrode, because this graphene oxide is insulating electronically, and when we shine the laser on top of that, and becomes reduced, and becomes reduced graphene oxide, and electronically conducting. So this is electrode. This is electrode, and actual SEM image here is this reduced part, which is electronically insulating, but this is not. This is ion conductor, but electronically it's not conducting. So this is our electrolyte, and so ion proton is moving, between those two electrodes. That's how we actually made it initially, but this is not that easy to make many. So what we have done is we actually coat this on plastic film, and then we use a diode laser, and we actually put this substrate on 3D printer, and actually we actually move back and forth, and then we scribe it this way, and then we use scissors to cut and made a connection in series like that. So we made 8 devices connected in series, and make one side hot, the other side is cold. So, and then we can raise the voltage a lot. So we total 8 modules. And as we connect the more and more sample and device, okay, here, okay, here, and then the voltage here, sorry, okay, voltage here is actually raised here up to 1 volt, as you can see, okay, here, and it's pretty large here, and okay, my computer is lagging. Okay, here, and only at the temperature difference of 14. Okay, it's not that high. So which is really good. And On top of that, when we connect a module and with a little bit larger temperature difference, and we can actually have a 2-volt, and which is now, in a range that we can operate the device without too much trouble. Okay, typical device requires like a 1 or 2 volt, so small electronics. So this is something that we can do. So we actually tested whether we can use this as power supply for some devices. So actually we made a device which is called electrochromic device, which means that this device change color when we supply electron. So this is what we call Prussian white, and so Prussian white becomes Prussian blue when we supply electron. So initially this is transparent, and then after we apply temperature difference, and then we supply electron, and it becomes a more bluish and darker and darker. And this kind of electrochromic device is actually used for smart window, and so that we can shut off sunlight, for example, like this. And so we actually demonstrated that well, this could be used in practice. That's what we have done. Okay. And so, but this is a 2 volt, but the thermal power, as you saw, is only 10 millivolt per Kelvin. We're not satisfied. 10 millivolt per Kelvin is still too many, too small. So we want to have an even larger. So then we need an additional effect. So what we did at that time is, we use a thermal hydro electrochemical method together. Okay, so we combine the effects, make a better device to have a larger voltage generation. That's what we have done. So in this case, what we have done is we made this polyaniline, and PSS is a copolymer. And we made this polymer, and then we drop cast on carbon steel. Okay, this is a carbon steel, is metal. And then this greenish color is a polyaniline PSS. And then this is acidic, and which means that it will corrode this carbon steel. So this is basically penny PSS here, right there. And then we actually try to add another effect called electrochemical effect. And so because of the corrosion here, and there's additional effects, basically it's very simple. We actually put that thing and we combine them together, we sandwich. And then what happens here is underneath of this layer, this becomes very porous here, becomes very porous. And then we can create, because of corrosion, and we can create the beta phase FeOOH, like a kind of a nanostructure, and becomes very porous. And then we can actually put a little bit of a moisture here, and because of the moisture, our corrosion becomes a little bit different, depending on the this moisture level. So we actually initiated hydroelectrochemical method together, along with the thermal. So that's what we have done. And so what happens here is when we have different water contents here on one electrode versus the other, and then we do have a different corrosion potential and make a potential difference very, very large. So because of the time limitation, I'm not going to go into too much detail, but we're just showing you that here is thermal to here is electron or electrical voltage conversion factor, and which is equivalent to S, which is the thermal power. And so you see that previously what I have shown is 10 millivolt per Kelvin. Now it becomes a 90. It's actually one order magnitude higher. It's really large. Then we need just only a few devices, and then make a device out of that, and it becomes fantastic. So that's what we have done. Okay, and so we actually tested here, and using the we've actually made a sort of fever detector because at that time it's still we have a COVID problem, right? So fever is sort of a problematic. So we just wanted to demonstrate. Well, this is the fever detector, and because whenever you have a fever, then you have a more heat generation, right? Heat dissipation from the body. So this is basically the device here. This is the current status window, and this is a sort of a color indicating, well, this is a fever. And so this is kind of a portable device that you can just attach to your skin and just show, well, this is my current status, so that we can actually easily detect who has a fever, for example. Or in the past, and there are a lot of diseases for cattle and swine flu, for those kind of pork meat, and we raise a lot of say swine, and the swine flu at that time was problematic in maybe several years back, and so we can attach those devices to those animals and to detect those kind of fever as well. So this is a normal condition, and the current status is okay. And whenever somebody actually produces more heat, then this becomes darker, and above this range, this becomes this indicate that, well, this person has a fever, like that. So we demonstrated that, well, this device can be actually used with only few devices connected, and we can actually make a actual device, working device out of that. And this is what we have demonstrated. So interesting thing here is that we only use a delta T here is only 2.9 degrees C, not more than that. It's very, very tiny, but still we can generate, we can operate this device out of this small temperature difference. So that's basically the topic that I want to cover. And the other half is about the energy storage using carbon nanotube. This is we use a carbon nanotube to make this device energy storage, but we convert the energy and we store. Here is just a pure electrochemical energy storage device, and what we call here is a lithium-sulfur batteries. These batteries these days are pretty hot, right? So everybody want to, these days use electric vehicles, and which requires batteries. So I'm going to talk about this. And Tesla these days a front runner, and China has also NIO and the other Xiaofeng, right, probably, and that kind of electric vehicles as well. And in the future, and we will probably need to use these electric vehicles because of greenhouse gas emission and things like that. So the problem that we encounter here is here, and cost. For battery, it's actually significant. It's 40% of electric vehicle. So now Tesla is most popular, but it's too expensive. And I really want to buy one, but it's too expensive to buy. So I wish that somebody can develop really low cost batteries. So I hope that we can actually develop that, and so that we can sell our technology as well. And this is basically the problem. Now, in that sense, people want to develop high energy density battery plus the low cost battery. So currently, this is lithium ion, okay, lithium ion here, which is really at the bottom. And this is now industry want to achieve that, but still is not quite yet. And now this is the magnesium ion. This is a lithium sulfur here is actually quite large here compared to that. So if successful, on top of that, the sulfur is really low cost. Okay, sulfur is not much usage, but whenever you produce oil, then you basically generate sulfur. Okay, you want to take sulfur out, so not much usage. So sulfur is very low cost, and what people actually use here is, NMC and or LFP, and in particular NMC requires those cobalt, and those things are expensive. So here's our objective is to obtain higher capacity, energy density, and then we can actually load more sulfur, which is the active material. Okay, and also another problem is that we have to cycle much longer, and we have to improve a cycle. And so one of the problems for lithium-sulfur battery is polysulfide shuttle in cathode, and we want to suppress this. And also, there is actually fire, and typically in lithium-ion battery, that is one of the main cause is dendrite, and we want to dendrite to be suppressed. So that's another thing that we want to suppress and minimize. So typically, what happens when we make a cathode is basically we use a carbon black or any carbonaceous material like graphene or graphite, whichever. We need an electron conductor, and then we use a sulfur powder, mix them together, and make a sort of a binder together and make a cathode. So that's typically what happens. So pretty simple. There's a carbon black, and sometimes people use a carbon nanotube and powdery carbon nanotube, and it's like that. So compared to carbon black, and carbon nanotube is actually pretty good in terms of, say, graphitic carbon actually has, and also in wire format, ensure pretty good electron conductor. So charge transfer is actually pretty good. But the problem is, if you just buy commercial carbon nanotube, and this is powdery, so you have to use a binder, glue together, put them together. The problem is that this glue here is insulating, okay? And then the electron cannot transfer. That's the problem, okay? And then you need to add more conductive additive, and as a result, this becomes problematic. So what we are actually using is we actually making carbon nanotube, and that are actually connected in this fashion. So it's basically 3D feature. Okay, so they are all connected. Okay, without too much trouble, and we don't need a binder. Okay, like this way. So, and then this can solve the problem, and I'll show you a little bit more detail a little bit later. And another thing that we are trying to improve here is the cycling performance. Okay, so this is a discharge curve of lithium-sulfur battery, and basically this discharge and then charge, and these are all different here. And these materials in between is actually soluble in electrolyte and become, they're actually moving around everywhere. And some of them actually lost, and this is actually problematic. Okay, so this is what we call polysulfide shuttle problem. And so during charge and discharge, they actually converted it in this way. And some of the material here is actually soluble, and they actually deposited here lithium anode, and then this becomes insoluble, and then this cell actually becomes very poorly performing. So this is one of the problem. Another problem is that when we have lithium is stripping and deposited, and they actually don't know their initial position, so that becomes like that. Okay, so when we have a large material, it's actually stripped and deposited, and then this really becomes problematic, because this one is it's not that problematic because it's not that sharpy, but this is a pretty sharpy, and it pokes through the separator, and then you have a short circuit and you catch fire, and this becomes really problematic. So we want to actually avoid that. So what we have done is we actually use this carbon nanotube to avoid these two problems. Okay, so this is our carbon nanotube. This is how we actually synthesize it. So we actually use a chemical vapor deposition method, and we fly this carbon source with the ion together, ferrocene together here, and then becomes a catalyst. And then when we grow carbon nanotube here, and we deliver this catalyst, and then where the catalyst is deposited, and another carbon nanotube grow, another carbon nanotube grow, and becomes like a tree, and becomes the entangled carbon nanotube. So this is our carbon nanotube here, and so it is actually freestanding, and so they are actually quite elastic. We can actually bend it this way and without too much trouble. So we don't need any binder here. Okay. So what we have done here is we use this porous media. Okay, and this porous, you see that is porous, in very elastic. No binder is required. So we actually made a cathode and the anode here with lithium metal, and then we use this polysulfide and embed it, and it's like that. Okay, so, and then we made a battery and we cycle. Okay, so okay, so the computer is okay. So as you can see here, this is a discharge capacity, and this is cycle number, and we actually ran about 800 cycle, so which is a decent. And 800 cycle, if you buy an electric vehicle, and if you run maybe a 10 years, use 10 years, then becomes maybe 600 cycles or something like that. So compared to current lithium-ion battery, and the energy density of our system is actually quite large, as you can see. Okay, so actually it's works pretty well. It's fantastic, and we are working on this technology for a long period of time. We have a lot more development, and in addition to this, and as of now, so one of the technique that we're using here is this carbon nanotube can be functionalized by making this a kind of trench. So what we are actually making here is a multiple nanotube, and we create this kind of trench, and then we put the carboxyl group and hydroxyl group, which attract the polysulfide, and then we have pretty good affinity to avoid polysulfide. So polysulfide is actually absorbed when we actually put the carbon nanotube sponge here, and becomes transparent from initial solution here. So they basically absorb all the polysulfide, and then we can avoid the polysulfide shuttle in this case. And so this actually works pretty well. And this is the basic procedure how we actually make it. But I will just skip it here. And so this is a microstructure here, and those are really trenchy here. Can make a trench, you can see that. And so we can actually functionalize those carbon nanotubes pretty well. And also this becomes polysulfide philic plus lithophilic, and also hydrophilic. And another thing that we are working on is we actually use this as a lithium anode, and we slice it. We slice this actually here, and these days my students can slice it about 100 micron thick. Actually, they are actually doing this pretty well. Using the razor blade, they can cut, and nothing is required other than the razor blade. And they're actually doing pretty well. Now it's slicing it, and we actually put the solid sulfur in between, and this is a cathode, and we press it, make a cathode. For anode is tricky, and we want to actually infiltrate the lithium inside. But it turns out to be, initially this was not that, easy. So I'll show you the video. And so this is a basically pristine carbon nanotube. And you see that the pristine carbon nanotube here. And this is a molten lithium. So we actually increase the temperature here, make it liquid phase lithium inside the glow box. And you can see that. So we try to infiltrate. We see that it doesn't get in. Lithium actually doesn't go in. It's pretty stubborn, and they're not getting in. Even if we press it, it doesn't get in. So carbon nanotube, pristine carbon nanotube, doesn't like lithium. So, but when we actually functionalize with this trench wall, and as you can see here, we just touch it, and it start to, wet and getting in. So the functional group on the surface is so informed, and so that we can change the property dramatically, like this. Okay, so we made those, materials, and we actually, made a battery, and we tested all the performances. And so this is an aerial density, and this is a capacity near 100th cycle. These are all literature value. These are our value. And so, and we have a much higher cell power, and we have a much higher, say, energy, cell energy. So we actually demonstrated that, our battery cell, it actually works pretty well. So this is another video that we actually, not only we developed this, devices, and actually we study what's going on inside. And this is an in operando study, which means that while we are operating the cell, we visualize what's going on. So this is our carbon nanotube electrode, functionalized carbon nanotube electrode. This is the lithium side. We're trying to infiltrate lithium, and so when we infiltrate lithium, and it becomes lithiated and becomes brownish color, which indicates that lithium is getting in, and getting in like this way. So this is what's happening. And so we visualize what's going on as well. And so we make sure that things are getting in, and so that we can make our device. So not only this, and we actually make a conventional cathode together with this anode, and we made a cell, and then now we actually completed the manuscript, and we are actually submitting this manuscript to a journal. And but not only that, we actually calculated the energy density, and actually this is better than the current commercial battery cell. So this is basically a similar thing. Okay, so now it's about 9:50, and in the U.S. time. So I just want to stop here, and I just don't want to bore a lot of students. So it's better to stop. And so basically, the take-home message that I want to deliver here is we developed simultaneous energy harvesting and storage device using two different approach, and one is in plane direction like that, and then using very scalable way and sort of a roll through process, and then we made this, and we cut, and we assembled the cell, and then this is a planar, this is a auto plane device. On top of that, and we added another effects called the hydroelectrochemical way. We boost up the voltage. And for lithium-sulfur battery, and we synthesize this kind of novel device, material, porous 3D porous carbon nanotubes found, and which is a binder-free and porous electrode, and we functionalize it, and we use this as a cathode and anode to make high energy density batteries. Okay, so that's basically all I want to say and for this presentation. Thank you so much.
Okay, thank you very much, Professor Yu. It's a very wonderful talk. You talk about both about the energy conversion and the energy storage. Yeah, it's very impressive.
Thank
Now
you.
now it's open for question and comments. Any question and comments from the floor?
Okay, Professor Yu, okay, thanks. It's very nice talk.
Thank you.
Yeah, okay. So even though I did not work in this field, but I would want to know something about this the thermal energy conversion to the charge or charge to the thermal convert to the charge, because now I'm also working on some work on the thermal conversion to the spin current, not charge current.
I see.
So I want to know, okay, why you do the measurement, okay, how you control the environments, okay, because this sometimes, okay, the measurements cause a very large, okay, the errors, okay, for the temperature difference and why you provide the energies, any comments for your measurements, okay, any know-how, any tricks, yeah.
Yeah. Temperature measurement is kind of most tricky part. Yeah, obviously, and so for a very accurate measurement, obviously, one of the important things that you have to avoid is radiation effect, and in particular, when you have sort of a in-plane device, whenever you measure it, and you have some radiation effect as well. And plus, whenever you measure, temperature on top of device, and then your bottom and your top, the temperature could be different. So those need to be overcome. Those measurement error need to be overcome, and that's kind of tricky part.
So how much our device? What device size? What's
device size?
Yes.
So for auto plane direction, and this is about the single device is about the coin size, and for about coin size, coin.
Oh, okay, coin size.
Yeah,
okay.
A single device. Yeah, so about that. And for planar device, it may be about single device about this size, and so it's not that big.
Okay.
And so typically about this size is about, say, you can just think that it's about the coin size.
Have you done some measurements on the thermal conductivity?
Thermal conductivity,
yes.
In plane direction or out of plane direction?
Both. Okay, sometimes. Yeah, both.
Yeah. Well, out of plane direction, yeah, we measure, and in plane direction is not that easy because of this radiation effect. And so we basically we conjecture and what kind of value that is, and for our device purpose, and we don't need to measure the thermal conductivity, so we didn't measure for in plane direction, but out of plane direction, yes.
Okay, so what kind of modules you have used for this measurement? Because maybe my device is quite small. Okay, I don't know how do you measure. Okay, for my measurement, for the thermal conductivity, we normally use the one resistivity bar, right? To either source and the sensors. This one. There sometimes make 2 bars. Okay, 2 bars. One is source, one is sensors.
Yeah.
So what kind of module you have used to make sure? Okay, definitely we can measure some results, but I want to make sure the results is more accurate as possible, right? So anything you want to have comments on this one?
Yeah. So actually, for very small, tiny materials, and my actually PhD thesis is about the thermal conductivity measurement.
Okay, good. Okay, as a red person.
Yeah. So basically, at that time, and what I have done is we actually maybe I can draw. I don't know whether I can annotate here. So basically what I did at that time is we actually had this kind of suspended heating device and the temperature sensor. So we have this heater module, and this is a resistive heater and plus the sensor. This is suspended, so there's nothing underneath. We have this, and so it's like that. It's like that, and then this two suspended device with a platinum resistive coil. And actually, I made this using microfabrication at that time, and this is suspended, so there's nothing underneath. And we made this device, okay, and like that. And then we actually put our material in between. And then this is one is a heating side, this is a sensing side, and we measured the thermal conductivity at that time. Okay. If the object is small, then the radiation effect could be ignored. And this is how we actually measure the carbon nanotube. And actually, I'm the first one actually who measured the thermal conductivity of individual carbon nanotube.
Okay, do you have any experience measure the thin films?
Thin film can be measured with that. And I didn't measure thin film, but at that time, and after I graduate, and other folks actually measured that. So thin film can be measured in this way. And actually, graphene film was measured using similar method. So that is, it's not exactly the same, but the similar method and the graphene was measured, and then that was actually published at that time as well. And so you can probably check those kind of technique, and which has been used.
In the Australian sunshine of the form separated in the middle of the factory in the daylight too. Then now shorter by 24 meters, 5.6 or 3.2 miles, or the array version of the human activation zone.
Excuse me, hello?
Yeah, I cannot hear. Okay.
Oh, maybe he forgot to, yeah.
Okay.
Yeah. Okay, thanks for you. Okay,
So those are the technique, and if you send an email to me, and then I'll probably refer some of the papers that you can take a look.
Okay, definitely. Maybe I got your email. Okay, thank you.
Mm-hmm.
Okay, Professor Yu, I have a question about the thermal hydroelectrochemical cell. For that cell, you observe the very high thermal power. Could you tell us a little bit more why the thermal power is so high? That result is very impressive.
Oh yeah, okay, I see. Okay, yeah. So because of all the, okay, let me see. Time limitation, I actually skipped a lot.
Yeah.
So,
yeah.
Let me see. Okay, so I didn't show a lot, and yeah, basically this is a working principle. Actually, I didn't show.
Oh, okay.
Because it's a little bit complex, and I just didn't want to bore a student. So maybe it's kind of boring, and so basically what happens is this, and so it is actually hydroelectrochemical, sort of effect. So when we have one side hotter and the other is colder, then the actual water is migrating, and this is more drier in the hotter side, and then the colder side, right? So it's drier. So more water is actually getting into this colder side.
Okay.
And so that's one of the reasons why this actually becomes maximized whenever we have a relative humidity of, say, 50%. And if it's, say, for example, every pore in the electrode is filled completely by water, then there is no difference between hotter and cold side. But we just need to have a sort of half filled. And then when water is actually putting, here is inside and the colder side and escaping from hotter, then the difference is maximized.
I see.
So what happens here is this is basically the potential and the crossover between two lines. This is what we call Evans diagram. And when we have basically if you can just think of if you have more water, then there's more corrosive environment. If it's less water, it's less corrosive environment. Because of that, this is a corrosion potential, and where you have two reaction here, those two reactions. This is actually reaction here, and the ion becomes oxidized, and this becomes reduced, and so those two lines meet at the center. This is a corrosion potential. So when we have a less water, then the becomes like this. Okay, this line becomes upward. And you have a new established voltage potential. And when we have more water, it's like that. So one side initially is same, both electrode. But once you have this hotter and colder, hotter side becomes that, less water, colder side becomes bottom. And then we have a temperature, voltage difference here. This is actually quite large.
Oh, yeah, thank you. So in terms of this mechanism, so if you use some other electrode material, if they can also have this kind of electrochemical action, you can maybe you can also observe a high thermal power.
Yeah, it should be like that. Yeah.
Okay.
Although this project is over, so I don't have any money to continue. So temporarily, we're not doing that because I don't, here in the U.S. Students cost a lot of money, and so that's unfortunate. This is the case, and I hope that Singapore is not the case. So
okay, thank you. Yeah, it's very interesting. Yeah,
thank you.
Yeah, is any more question? Any other question from the floor? Okay, I think now it's past 10 p.m. in Texas. Yeah, so let's thank Professor Yu again for the very wonderful talk. Yeah, thank you. Yeah.
Thank you, Professor Yu. Thank you very much.
Yeah, thank you for the invitation. All right.
Bye.
So now, how is the situation in Texas, Professor Yu?
Yeah, well, we're actually back to normal. And
okay.
Yeah, although, because of COVID and makes our life really more difficult, but we have, back to normal, kind of no mask, kind of, we have a regular lecture and in class, no Zoom anymore.
Oh, yeah, it's good. Yeah, Singapore is, we almost back to normal.
Oh, is that right? Okay.
Yeah.
Good. Yeah. I hope that the COVID stuff goes away quickly.
Yeah.
Really bad. Yeah.
Really
okay.
bad. Yeah. Okay. Thank you very much. So
right.
I believe I will see you in future. Yeah, in conference. Yeah.
I hope. Yeah. Okay.